Many users interact with ChatGPT as if they are consulting a single unified brain. But beneath the conversational surface, there is no solitary thinking machine. The application is a composite of distinct, interlocking mechanical layers working in unison. It can converse, translate, and analyze documents with a remarkable degree of human-like versatility. However, the mechanical reality bears no resemblance to a biological brain or a digital replica of the human mind. The term ChatGPT describes a product wrapper, not a permanent or single neural network. It is an evolving system that can change its underlying models and tools depending on the date, subscription, or specific user request. To understand modern frontier models, we must separate the underlying base model from the scaffolding of tools, memory, and safety routers forming the system envelope. Recognizing this separation explains how a statistical engine designed to predict the next token can eventually execute computer code and solve discrete geometry conjectures. The model operates on tokens, distinct subword identifiers, rather than whole words. A tokenizer converts user text into these sequences before the model performs any calculations. This 3D space represents how the model handles those tokens. Each identifier becomes an embedding, a long vector of numbers. This allows tokens used in similar contexts to acquire similar mathematical representations, generalizing beyond training data. Because word order determines meaning, sequence data is injected into these vectors to distinguish the dog chased the cat from the cat chased the dog. Translating text into this spatial coordinate system allows the system to mathematically map contextual relationships across a massive numerical landscape. These embeddings then pass through multiple transformer layers. Unlike older systems that process text in order, the transformer uses an attention mechanism that processes many positions in parallel. In this grid, the model calculates 3 representations for each token: a query, a key, and a value. The intersection of queries and keys determines how much weight positions give each other. During text generation, this attention is causally masked. A shadow ensures the model only uses preceding tokens, mathematically blinding it to future sequences. After feed-forward operations, the final representations resolve into scores for every token in the vocabulary. A softmax operation turns these scores into probabilities, allowing the system to select the next token in the sequence. Reducing prediction errors across enormous datasets forces the model to construct deep internal representations of logic, terminology, and syntax. This allows it to generate plausible continuations across many domains. Constructing a model begins with pre-training. Massive quantities of public information are funneled into the network, distributing regularities across billions of numerical weights. This phase produces a base model. It is not a conventional database or a searchable archive, but a statistical engine capable of predicting text. While it doesn't store documents, it can sometimes memorize and repeat vulnerable training passages nearly verbatim. If you ask a question, it might respond with a question or imitate a forum discussion, rather than providing a helpful answer. Reinforcement learning from human feedback, or RLHF, turns that statistical engine into a cooperative dialogue system. As shown here, a reward model supplies a training signal that changes the language model's internal weights based on human preferences. This happens during development, long before a user sends their first message. The conversational style and behavioral guardrails of the AI are engineered products of these training choices, rather than incidental properties. When a user submits a prompt, the application constructs a larger input. It combines the user's message with system instructions, conversation history, and data retrieved from external tools or memory. The model adapts to these instructions through in-context learning. This functions as temporary working information and does not rewrite the frozen parameters of the underlying neural network. Modern systems also employ dynamic routing software. For example, the GPT-5 architecture can dynamically assign a request to a faster general model or a deeper reasoning model based on task complexity. The language model acts as a coordinator for external tools. It can invoke Python to perform exact calculations, use web search to find current news, or extract data from uploaded files. The final answer's reliability depends on the entire system, whether the correct tool was selected, the source was reliable, and the model interpreted it accurately. By 2026, AI began solving research-level mathematical problems, including a verified resolution of Erdos problem 728. While early chatbots often failed at arithmetic, specialized systems reached gold medal standards on the International Mathematical Olympiad. These breakthroughs didn't come from simply scaling up next token prediction. They required a transition from general text generation to a framework that separates proposing an idea from verifying its logic. An LLM proposes a candidate solution in a formal language, which a trusted software kernel checks step by step. When the verifier identifies a gap, the LLM revises it. This iterative loop continues until the proof passes, building on successful outputs. Strict external verification acts as the ultimate safeguard against hallucination, the tendency for models to produce confident but false information when internal evidence is weak. The era of relying solely on parameter scaling is ending. Progress is now multidimensional, driven by better data quality, specialized post-training, and systems that can devote more computation to individual problems at inference time. The evidence defines this as a trained computational system, one extended beyond its fixed parameters by rigorous systemic scaffolding. The most consequential shift in the industry is the move away from chatbots that generate immediate answers. We are entering the era of autonomous systems, built to continuously propose, test, and document complex solutions.